Let's have a look at Da Vinci's ellipse drawing device. If you want to draw a circle, well, you can use a compass. That's one way to do it. If you want to draw an ellipse, well, there's that trick that I think we've all seen using string. Use some string and 2 thumbtacks. That's one way to do it. But what if you're given A and B, the semi-major and semi-minor axes of the ellipse, and you want to draw an ellipse precisely with that A and B? Well, there's this very clever method that is purported to have been invented by Leonardo da Vinci, the Da Vinci machine, or Da Vinci device. It's I guess you can make it automated into a machine. And this is what we're going to look at today. It's quite interesting machine, and we'll look at the mathematics of it and see how it works. So this is part of it. We have this box here, and these are axes. This is your X and Y axes. This is the Y axis, X axis, and here we have this bar. It's like a rigid bar, and this point P is where you put your pencil. So P, this is where you put your pencil, and point A is fixed. Well, it's not fixed, it's just that it can't move off this vertical axis, and point B has to slide around the X axis. So yeah, you can move the bar around. What you can do is move B this way, okay, to B prime. And if you do that, well, A is going to descend a little bit, and you get A prime here, A prime. And P is going to move out somewhere out here somewhere, P prime. So it's going to move something like this. It's got to stay straight, something like that. Well, it's not very straight, but I think you see what I mean. We'll look at another picture. So A, this is moves along the y-axis, and B, this moves along the x-axis. Now, this is very interesting. So here, let's call this little a, this length, and this length here, we'll call this little b. So AP, this is A, and BP, this is little b. And this will turn out to be your semi-axes of the ellipse. So this is a very, very convenient way of drawing an ellipse. We will see how it kind of works more dynamically in a few seconds. But all you have to do is adjust P. Place your pencil somewhere along this rigid bar. There's maybe a movable thing here where you can put the pencil in there like a holder, and that will set your A and your B, and you'll be able to draw part of the ellipse. Okay, so here's a few more frames of this, or sequence of motion. So here's the P1, and here P2, and here P3. So what I'm doing here is I'm sliding this point to here, and then I'm sliding all the way out to here. And of course, this has to go down a bit, and then down some more. This one here is the vertical point A, this point A, and so on and so on. Okay, so this is kind of something that you would imagine will produce a curve, and you can easily imagine it completely wrong. Okay, so let me erase a few things here, and I'll show you how you can do it wrong. And this is, in fact, what I was thinking a long time ago when I looked at this. We take this point here, and as we move this end, slide it along X. As we do that, we tend to imagine this is going to go down like this. And there we go. We have some kind of, let's say, 1/4 of an ellipse this way. And that's intuitive, you know. But okay, it's intuitive, but this is wrong. And I'll show you an easy way to see why this is wrong, and by putting up another photo. So here it's easy to see what's gone wrong. The point P lands here. It doesn't land out here. So this is wrong. It doesn't land out here. It lands over here. So it's close. This is distance A, you see? And so it's not possible to make this kind of curve. What ends up happening is this slightly counterintuitive curve going down like this. If I can just draw it well, something like this. And this is actually, by the end of this video, we're going to draw some very nice versions of this. So right now it looks pretty bad, but this actually is part of an ellipse. Okay, so that's what's going to be traced out with your machine. So you're going to build this little box out of like a frame, like a metal frame, and slide this bar along with your pencil, and it will produce a nice ellipse. And then before we continue with the question of how do you produce all of the ellipse, let's prove that point P is indeed on an ellipse. And we will actually show that it's on an ellipse with semi-axes, okay? With semi-axes A and B. And in fact, we'll show that the semi-axis in the Y direction is going to be B, and the semi-axis in the X direction is going to be A. We're going to show this. So let's label this P, and we will give it coordinates big X and big Y, like that. And this here, from here to here, this will be little a. This will be you'll see it's our X semi-axis. You'll see that soon. And this here is B, okay? And so along the bar, well, that doesn't change. This is also A, and this from here, from P to this point here, this is also B. That doesn't change because the bar is rigid. Next, let's call this little x, this distance here, how much the slide is in the X direction. And of course, we want the same here. This is going to be the slide in the Y direction, okay? So little y for this. And we can use Pythagoras law now to make some relationships. Little x is our parameter, little x. Let's say we slide it by little x, so that's an independent variable. And y, by Pythagoras rule, is the square root of a plus b all squared minus little x squared, like this. Maybe just a simple application of Pythagoras rule. There's no need for any trigonometry or anything like that. Now, a very important technique. Suppose I have a segment between 2 points, A and B, and I have some point in the middle, P, and there is some proportion here, like this is A and that's B. So what is P? This is a very important theorem in geometry. It's called, or a technique, it's called division of segments. It's a very, very important thing. You should always remember this. So P is B times A plus A times B over A plus B. Now, let's try to see how this works. Now, it's a bit counterintuitive. You think, well, it should be A times A, but no. If A goes to 0, watch. If A goes to 0, then P must become A. So let's see if that's true. Then P, B, okay, A is 0. So I have BA over B, and that's A. So that's good. And now if B goes to 0, then, well, P will go all the way down to B. So B goes to 0. P is AB over A, and that's B. That's okay. And now what happens when A equals B? Well, when A equals B, then P will be right in the middle. So it should be the midpoint. So P is A plus AB over 2A, and cancel out the A, we get A plus B over 2, and that's good too. So this formula is a really great thing, and you should always remember this. It's very, very handy. So we're going to use this now with our X and Y. So let's look at point A. Point A was the A and B were the endpoints. Capital A and B are the endpoints, A and B. So capital A is constrained to move only on the y-axis. So this is 0, y. But y, we have solved for y here. Okay, so this is 0 and square root A plus B all squared minus x squared, like that. And now B is much simpler. It's constrained to move on the x-axis only, so that's x0. Okay, very good. So we're almost ready to plug stuff in. So P, we give it capital X, capital Y as its coordinates. This will be BA plus AB, the division theorem, over A plus B. And now I plug these things in. We get B0 and this from here, square root A plus B all squared minus x squared. And this plus A x0, that's B, and over A plus B. Very good. So we can actually solve for big X. Big X is what? Well, okay, so there's no x component here. Here there's no x component. The x component is over here. So it's A, x, okay, I don't need the parentheses anymore, over A plus B. And now capital Y, Y coordinate of your pencil is B times square root A plus B squared minus x squared over A plus B. Now, if P is on an ellipse, then it has to satisfy the ellipse equation. Then we have to have x over, let's say, A squared plus y over B all squared must be equal to 1. Now, I'm taking a guess that it's A and B here, but it could be B and A. So let's think about this. Which way is it? Well, let's go back a bit. We see here that B, our pencil is going to be right here when we begin. So the longest in the y direction is going to be B. That means the semi-axis in the y direction has to be B. And if we go to this picture here, all the way back here, the semi-axis in the x direction has to be A. That's the farthest that this pencil is going to go in the x direction. Very good. So I think the first guess is the good one, and it's not really a guess because we see it in the picture. And let's see if this works. Right, so let's plug in big X there. We have A squared x squared over A plus B squared, but we have an A squared also there. And now let's do Y. So we have B squared, and this becomes a bit nicer. A plus B all squared minus x squared. The root goes away. A plus B all squared, and there's a B squared here. Okay, and this equals what? Well, this stuff cancels out. Some of this cancels out. This and this cancels out, right? So I have x squared plus a plus b squared minus x squared over a plus b squared. Haha, look at this. This cancel with this. So I have what? I have a plus b all squared over a plus b all squared, and that's 1. Yes. Okay, so this really works. The Da Vinci method really works. This really is an ellipse. That's amazing. So P is indeed tracing out an ellipse, or at least part of it. And how do we get the rest of the ellipse? How do we get the whole thing? How to draw the whole ellipse? Well, this takes a bit more Da Vincian ingenuity here. Okay, so we start with our bar. I'll use some color. We start with our bar here. We slide it this way, and it falls down onto the x-axis. And now we can just keep sliding. Let's slide it down this way. You see, it's going to come back and become vertical again. Okay, so we just keep sliding this part along the y-axis, and it becomes vertical again. So that takes care of this quadrant. This will draw out yet more of the ellipse, you see, and I can keep repeating this process here in this quadrant and then this quadrant. So you can build a really cool little machine like this with let's say a metal cross and then a movable bar that slides around somehow. And if you do that, send me some pictures. I'd like to see it in action. That would be really cool. All right, so let's look at some results of what happens if you use this the full Da Vinci ellipse machine. Let's see some results of this. Here is one case where here A is smaller than B. So the semi-axis in the x direction here is small, and the semi-axis in the y direction, B, is bigger. And we get this really pretty construction like this. So what happens when A is actually bigger than B? That's going to be interesting. Here is the case where A is bigger than B. So here A now is slightly larger, large enough that you can see the difference in the axes. So here now the semi-axis in the x direction is bigger. You see, this is A, and the semi-axis in the y direction is smaller. And okay, so this is when A is bigger than B. And now what happens when they are equal, when A equals B? Can you take a guess what we should obtain when A equals B? Well, I'm sure you can guess, right? Let me fetch the picture. That's right. You get a circle. So now both are the same. A and B semi-axes are the same, and you get this beautiful, perfect circle. Very lovely. Well, I think that's really cool. I think the Da Vinci machine is totally awesome. And the mathematics behind it is really, really nice. And I just love the way it all works out. It's just so beautiful. Well, if you liked this video, then click like. That helps. And please subscribe to my channel, and I will be making more interesting videos. I think the next one is probably on geometry again. There's just so much interesting stuff to do with geometry. If you can build one of these ellipse machines, then take pictures of your results and send them to me. I would be really happy to see it. All right, that was it for Da Vinci, and I will see you next time.